Hi, and welcome to another discussion of weather radars. We're working our way through all the different components of a radar. We've got one last component, and that last component is the display. And this is probably the most important because this is how we interpret radar information. So what radar displays are available? There's many different kinds, but they tell us about the power that's coming back to the radar, the location, and they give us information about the intensity and also the elevation angle and also the distance, and as well as the azimuth in some examples or some cases. So we're going to look at three different types of displays. Actually, there's a fourth one also we're going to cover. We're going to look at the very old one, which is called the A-scope. Then we're going to go through the one that's more common, which is PPI. Everybody uses PPIs, but they don't know what they're called. And then look at range height indicators. And finally, I think we're going to talk about the time height diagram also. So first, the A-scope. This is actually the very first, very original way of displaying radar information. Basically, it's an oscilloscope. And what it measures the time that signals are returned from a pulse that was sent out. And of course, time is a function, or time is equivalent to distance if you know the speed of the signal going out and returning. And then also they indicate on the A-scope the power that's coming back to the radar, and that's the amplitude. So each pulse is shown, and you can look at it and see where the strongest power returned is. So here's an artist's rendition of what an A-scope looks like. But basically on the left side, that's where the radar is located, and then everything to the right is farther away from the radar, so that's time or distance. And then the green line indicates the strength of the return, so you can see there are returns from the ground and also from weather. The weather return will look kind of fuzzy because there are a lot of little raindrops or crystals or other hydrometeors in a cloud, and they're constantly moving. So it looks like that green line is kind of moving and kind of fuzzy. Actually, the ground targets don't really move all that much, and they're usually pretty solid. So it's easy to detect from weather echoes from ground targets. You don't see A-scopes anymore. They were popular up until probably the 1970s or 80s, and then everything went digital. When everything went digital, we got color radar. And PPIs have been around for a long time. They actually were very similar to the old black and white TVs in some respect because they are a phosphorus screen that was energized by an electron beam. Nowadays, they're all plotted. The information is plotted using digital signal processing. So in other words, you get colors, and the colors help you identify the intensity of the radar echoes. So of course, the PPI is just like a map. It's circular. It's got range rings. Usually, east is to the right, and west is to the left, north to the top. And then the range rings give you a distance out to echoes, and the intensity is shown nowadays by color, but in the old days it used to be based upon the brightness of the phosphorus, how bright it shone. And that was kind of difficult to determine the intensity. These days with signal processing and color, it's really nice to figure out. It's really easy to figure out. So here's examples of PPIs. Here's radar down in Florida, and you can see the radar. I think this is at Key West, it looks like. But of course, you got range rings. You've got also a map, which sometimes is superimposed upon the radar. In the older radars, you never had a map, so it's difficult to find things, locations on the PPI. And then, of course, the colors indicate the strength or the reflectivity of the radar returns. Here's another PPI, and this one is out in Kwajalein, and it looks like there's a typhoon bearing down on Kwajalein. Kwajalein is in the Pacific, and of course you can see the intensity in different colors and determine the distance and the direction where the hurricane is located. RHIs are range height indicators, and what they do is they're kind of like PPIs, but they're in vertical. Instead of looking down on a map, you're looking vertically through the atmosphere. So it's a cross section of the atmosphere, or in particular, when you're looking at a radar target, it's a cross section through perhaps maybe a thunderstorm or through other types of precipitation echoes. So it gives you a vertical profile along a particular azimuth. In this case, the antenna scans up and down with the PPI. It was going round and round, going up at different elevation angles. So here it's going up and down. You stop along one azimuth, the radar antenna goes up, it comes down, and then you can plot this information on a vertical cross section that shows along along the bottom axis distance, along the side axis or the y direction, you'd have the height. And of course, the intensity nowadays is shown by color. In the olden days, when we had a phosphorus screen, it was how brightly it shone. So here's an example of an RHI, and I think this is from the University of North Dakota radar. This is, I'm not exactly sure where this is, but that looks just like a thunderstorm. And you can see they're doing a cross section or a slice through it. The bottom picture indicates reflectivity, and the top is indicating the velocities. So this is a Doppler radar, and shows up pretty well the intensity of the hail shaft, and also you can actually see the anvil of this thunderstorm also, and that shows the range and also shows the height going up in kilometers and range going out from the radar in kilometers also. And this is along the 309 azimuth, which is to the northwest. So there's your radial velocities, and there's your radar reflectivity, in other words, your DBZs. Another type of diagram is your time height diagram, and this is used if you have a vertically pointing radar. Radar is pointing straight up, and there are some radars like that, like cloud radars, KU or KA band or K-band radars, where they're just looking straight up. The radar doesn't tilt at all, just waits for clouds and also precipitation to move over that. So the time height diagram gives you, of course, height or intensity echoes, how high they are up in the atmosphere. And then along the x-axis, it'll plot the time. In other words, when the echoes moved over the radar. And this is what time height looks like. And they've got several different parameters here. They got the Doppler velocity, spectral width, and also reflectivity. So this is showing probably some precipitation or some convective elements moving over a radar. In particular, this is a TRIM radar, I think down in Brazil. And here's looking a little bit closer, the height and also the time, showing the reflectivity. And then here's another example from another radar in particular. Oh, I take this back. This is the TRIM satellite. It's not a radar on the ground, but actually it's a satellite passing over a particular storm and looking at the cross section. Kind of like an RHI, but the radar in this case is actually moving over the ground. So those are a couple of different displays, and I think we're finally done with components of radar. Next time we're going to get into the radar equation. If you like equations, stick around and watch another video.